Here is a recording of questions 31 through 40 from the practice test for 5.5. It says the radius of a circle is increasing. Let me write that down. dr dt is greater than 0. All right? At a certain instance, the rate of increase in the area is numerically equal to twice the rate of increase in the circumference. And dA dt is equal to 2 times dc dt at some point. What is the radius of the circle at that instance? So it looks like we've got a bunch of things. We've got an area changing, circumference changing, we got radius changing. Let's write down some equations. How about that area is pi r squared? And therefore the derivative with respect to time is dA dt is equal to 2 pi r dr dt. Okay, so how are we going to use dc dt in this? Well, let's write down a formula that has c in it. That circumference is 2 pi r, and therefore dc dt is equal to 2 pi dr dt. Now let's see, what do we have? Well, we can solve this for dr dt and replace it back into here. Let's try that out. So if I solve for dr dt, I get 1 over 2 pi dc dt is equal to dr dt. And so I'll go back to this equation, 2 pi r, and dr dt gets replaced with 1 over 2 pi dc dt. Okay, the 2 pi's cancel, that's nice. Oh, here's another replacement we can do. dA dt can get replaced with 2 dc dt. So now I've got r times dc dt is equal to 2 dc dt. Those divide out. Oh, that means radius must be 2. Let's go to problem number 32. This is an implicit differentiation problem. So let's start by taking the derivative with respect to x of both sides of this equation. And the derivative, that's going to be, the first thing is going to be a product rule. So first times the derivative of the second plus the second times the derivative of the first minus 3 equals 3y squared. Don't forget the chain rule for that y. All right. Now, most of the times what we would do here is we would solve for dy dx. But since they want us to do this at a particular point, what I'm going to do is I'm going to plug in that point right now. 2 times 2 times negative 1 minus 3 times 2 squared dy dx. So I've got negative dy dx minus 4 minus 3. And on this other side, I got 3 times 4, which is 12. So let's, oh, I'm sorry, this is negative 1 squared, that's a positive. Let's subtract dy dx from both sides. So I get negative 7 is equal to 11 dy dx. So let's divide by 11. And so we get negative 7/11. So the answer is A. Now I'm sorry, for number 33, I didn't give you enough room to do your work. But first of all, we're limited to x being greater than 0. And it's asking about increasing and decreasing behavior and concave up, concave down behavior. Let's handle the decreasing and increasing behavior. When does this expression negative or positive? Well, if x is greater than 0, then the bottom is always positive. So really we're just asking, when is natural log of x equals 0? And that is when x is equal to 1. So let's create a number line for f prime at 1. And I think it's pretty clear that it's positive when I'm bigger than 1 and negative when I'm less than 1. And these are all being greater than 1. And so the decreasing answers can't be right. And this one has from 0 to e. So that one can't be right. So we're down to C and D right now. Now what about f double prime? In f double prime, the bottom is always positive. So really we ask the question, when is 1 minus natural log of x positive or negative? So let's set that equal to 0. That means 1 is equal to natural log of x. And that happens when x is e. So when x is e, we're at 0. When x gets really big, this negative gets big. So it's like negative here and positive there. And our thing's about being greater than e. So I'm negative, so I'm concave down. So C must be the right answer. In number 34, we have a classic FTC Part 1 question. Let's remind ourselves that Fundamental Theorem of Calculus Part 1 says that if I take the derivative with respect to x of the integral from some constant to some function of x of f of t dt, I get f of g of x and then a chain rule. So in this case, I get 2x squared minus 2x, and then I've got the chain of 2x, which is 2. And that's f prime of x. F prime at 2 is the square root of 2 times 2 squared minus 2 times 2, all times 2. So that's 4 squared, which is 16, minus 4 times 2. That's 2 times the square root of 12. So the answer is E. Number 35. So number 35 reminds us that we really need to remember all of our derivative functions. Let's remember that the derivative with respect to x of inverse sine of u is equal to 1 over square root of 1 minus u squared, and then a chain rule. So in this case, our answer is square root of 1 minus 5x squared, and then our chain is a 5. And we can see that that's equal to E. Number 36. So we're given some information about the f between 0 and 3, f between 3 and 5, and then we have to do this integral. Let's break down that integral using some of our properties of definite integrals. 2 there. All right. First of all, I can break it down on the addition subtraction part. Antiderivative of 3 is 3x, 0 to 5, which is 3 times 5 minus 3 times 5 times 3 times 0, which is 15. That completes that strain. On this one, how about I pull out a 2, and then I'm going to note that from 0 to 5 is 0 to 3 and then 3 to 5. So this would be the integral from 0 to 3 of f of x dx, plus the integral from 3 to 5 of f of x dx, which is 2 times 6 plus 4, grabbing that from the problem stem, 15 plus 2 times 10, 15 plus 20, for a total of 35. And that's problem number 36. Problem number 37. I've got this area of the curve, the left Riemann sum, the right Riemann sum, and the trapezoidal sum are used to approximate that function over that interval using the same number of subintervals. Graph of the function is shown above. Which of the sums given underestimate? Well, if I try to left sum, that looks like an underestimate. Let's do 3. If I try to right sum, that looks like an overestimate. Now, for the trapezoidal sum, I'm just going to use one interval. Jump. And that clearly also is an underestimate. So I'm looking at 1 and 3. Number 38. If f is continuous on the closed interval from a to b, which of the following must be true? Please note that they did not say that it's differentiable. So maybe that's going to have a play in this. Are we guaranteed that we have a 0 in there? No, I can think of continuous functions that don't have zeros, so that can't be the answer. There's a number c such that f of a has got to be lower than it, and f of b has got to be greater than that. Well, what if the function's decreasing? If that was the case, we wouldn't be able to satisfy that. C, there's a number c in the closed interval such that f of c is greater than or equal to f of x for all x. That's our definition of an absolute max. And are we guaranteed an absolute max on a closed interval? Yeah, it's called the extreme value function theorem. And that looks like a good answer. But let's check the other two. There's a number c in the open interval such that f prime of c is equal to 0. Are we guaranteed a horizontal tangent for every continuous function on a closed interval? I don't think so. And last one, there's a number c in the open interval a to b such that f prime of c is equal to the average change. And I think that's the mean value theorem, but I also think that the mean value theorem says that you have to be differentiable on open A to B, and I don't have that given, so that's not true. So I'm going to go with C on that one. 39. The graph of f prime, the derivative of f is shown above. On which of the following is the interval decreasing? Let's see. I have decreasing behavior when f prime is less than 0, which happens here from 0 to 2, and here from 4 to 6. 0 to 2 to 4 to 6. The answer must be E. This function is continuous and differentiable. That's good to know. On the closed interval from 3 to 7, the table gives selected values of f on this interval. Which of the following statements must be true? The minimum value is 12. Well, certainly the smallest value in this table is 12, but could it go lower than 12 and then back up to 16 and still be continuous and differentiable? I think that's a possibility. So I'm going to get rid of Roman numeral 1. There exists a C from 3 to 7 such that f prime of 0 is equal to 2. Well, the mean value theorem does play in here. And if I look at f of 7 minus f of 3 over 3 minus 7, you can see that those two values are equal. So that equals a 0. So I think there is a f prime in that interval that's equal to 0. I'm going to give that a check mark. F prime is greater than 0 from 5 to 7. Well, that assumes that it's always increasing on that interval. And while these numbers do, 12, 16, 20, increase, there's nothing that says that it can't decrease then increase. I don't think that's necessarily true. So I'm going to go with B only.